introduce today's speaker, Lucy Vinette from Montreal. Not exactly Montreal.
University of Montreal.
Yes, yes.
Yes, you're right.
But what is CMB?
I will tell you. I will tell you.
Yeah,
Okay. So, well, thank you very much. You're very kind. I really want to thank you and Hun for arranging this visit and you all for attending. I've seen many of you in Montreal, actually, some of you in Montreal, not so long ago for a workshop in honor of our friend Gordon Semina. And I was coming here on, I'm also, as a researcher, and I've been a long time a director, but I'm a member of the Centre de Recherche Mathématique. CRM stands for that. It's one of the math institutes in Canada. But now I'm also in charge of this large institute, there's 2,000 researchers, called IVADO in artificial intelligence. And artificial intelligence was in this case, the main reason for my visit to Korea. But I'm really glad that you're giving me the chance to talk a little bit about research and the topics that I work on. So thank you very much. It's actually my fifth time in Korea. And I came here the first time in '85. Many of you were not born. And Korea has evolved enormously since that day. And when I gave my first talk, I had learned the Hangul letters, and I had tried to write my title in Hangul, but it brought me a big laugh from the audience. And I did not try to do that again, in part because I've forgotten what I had learned at the time. So it's a great pleasure to be here. Thank you for giving me the occasion. I will talk, hopefully in a pedagogical way, about interesting topics that are related. The main focus will be entanglement. This is an important topic. But I will see or establish connections with fields that are a priori different, and I hope you'll learn things, maybe not directly related to what you work on, but nevertheless, from a cultural point of view, I hope you'll enjoy some of it. Work has been done, so senior people are Nicolas Crampé, who's in France, and Raphaël Nepomniachtchi, who's in Miami. These are Gilles Paré is a postdoc in Montreal. He's a graduate student, and there were other people. This is a summary of 5 or 6 papers that I pulled together. Okay, so, whoops. Oh, yeah, now it does work. So, I'll deal with a simple system, free fermions, because they are a very good lab to study entanglement, the entanglement of many-body systems. So we'll focus on that, and then we'll see what we can say about the entanglement property. The main idea, as you know, is you take your system, you have to take it in a certain state. So we'll use the ground state, the state the full system is in, and you split it into parts. It could be many parts, but we'll keep that simple. We'll split it into parts, and then you want to explore how one part is entangled with the complement. So that is the general task that we want to discuss. And so to be concrete, I'll start with chains, and towards the last part of the talk, I'll look at fermions on graphs, more higher dimension. But to start with, I'll look for that type of chain, which is there. So you have hopping from one side, so the sides are labeled by little n. They run from 0 to n to big N. You have an n plus 1 here. And so these would be the kind of magnetic terms, and these are the hopping terms. These are the parameters, but they can differ from side to side. So they can depend on the side. So this is why I call these chains inhomogeneous. It's free because it's quadratic, and this matrix here will be important, lambda. The symbol will recur. And it's just a rewriting of this Hamiltonian with the three diagonal matrix, lambda. So we're dealing with fermions, so these C's are creation and annihilation operators that obey the usual anti-commutation relations. So this is our Hamiltonian to start with. Very
So considering periodic chain,
I don't know, it's a finite chain,
finite chain.
just a finite chain.
What is the boundary condition?
The boundary conditions are, well, you see, at some point I will assume that J minus 1 is 0, it truncates, but it's just finite. It's defined for the sites 0 up to big N. That's all.
Can you comment on boson case?
On?
Free boson rather than.
That's interesting. We've not done that. You'll see that it's something I want to do, actually. Some work has been done, but some things that I will talk about are similar, others don't have an analog. You'll soon see. Okay, so, well, we want to diagonalize the Hamiltonian, and the way to diagonalize the Hamiltonian is to diagonalize lambda. But lambda is a three-diagonal matrix, so it will be diagonalized with orthogonal polynomials. This will be the transition matrix. So there is in this basis, in looking at that, so the omega, there will be two bases. The one that defines lambda, right? So the position basis. So where the matrix elements are defined by this. So these would be the characteristic vectors. So with a one only at the site. So I will call this the position basis. And then I'm talking about diagonalizing lambda. So we'll have the eigenbasis omega k of lambda. And of course, I have the overlap of one basis over the other. And these would be the wave functions. And these, as I said, are the transition matrix elements, which will be basically orthogonal polynomials. So all the bases, these two bases are orthonormal. So the transition matrices will be orthogonal because everything is real in what I'm doing. And so if I factor out the ground state, this chi 0 will start at 1. And these will obey three-term recurrence relations with an initial condition like this. So they will indeed be orthogonal polynomials. So nothing fancy here, just diagonalizing this lambda with orthogonal polynomials. But these orthogonal polynomials will play an important role in what I'm saying. So I'm just reminding you again of what we have. These wave functions are orthonormal. If I pull out the ground state, this will then act as a weight for these polynomials of a discrete variable. Okay? All right. Then you can just make a canonical transformation, transform the initial annihilation and creation operators using these phi's, and you'll get operator C tilde. And it's easy to see that this will diagonalize the Hamiltonian so that in this form, in this diagonal form, so that if you define the vacuum, I will use double bracket to distinguish the states of the finite dimensional matrix from the many particle states. So if I define the vacuum as the one being annihilated, as usual, by all the annihilation operators, the eigenstates of the Hamiltonian will be obtained just by acting with the creation operators corresponding to those. And of course, the energies, it's a linear problem, will just be the sum of the eigenvalues of the matrix lambda. Okay, so we have done this very simple task of diagonalizing our Hamiltonian. Okay, first thing. So first part of in this section, I will set up the problem of computing the entanglement. You know, what do we need to do with the definition I've given? So we need to start by putting our system in a given state. So we'll put the system in the ground state. What is the ground state? It's a fermionic system, so we need to fill the Fermi sea. This is where there's one difference already with the bosonic case. So we fill the Fermi sea, so we put in the vacuum all the states that have negative energies. This would be psi 0, the ground state. What is relevant is to compute the two-term correlations. And well, this is defined by this, and it's an easy computation to see that it will be given by this form where k, the index here, runs over the indices that are in the Fermi sea. The k's are such that the omegas are negative. You sum over those k. This is the correlation matrix. You can do this mentally. Okay, now I will just remind you what were these phi's. They were just the overlap between these two bases, the position basis and the energy basis. And so I can write this matrix, if I want, as an operator, which is just written like this, because if I put m, the draw m and the ket m, I will recover this. But what is this? This is just a projector on the states, the energy states that are in the Fermi sea. This seems very simple, but the fact that the correlation matrix is a projector will recur, will come again. It's a point to remember. Okay, I want to talk about entanglement, so I should split my system into parts. So I'll take the first L+1 sites to be part 1, and the remainder as part 2. Okay. So it will be, and I take the system, as I said, in the ground state. To do any physics, so the system is described by this density matrix. It's a pure state, so this is what it is. And to describe the system 1, everything is contained in the reduced density matrix. So I trace over the part 2 of the initial density matrix. So if I know this, I know everything there is to know about the system 1, and I should get the entanglement in particular out of that. Okay. Now there's something, if you know it, it's very well known, but if you're not working in the field, it might not be so familiar. It's something called the Peschel's trick. And it says that ρ1, which would be a 2 to the L+1 times 2 to the L+1 matrix, right? Because I have L+1 site, each one can take 2 values, so it's exponential in that sense. Well, the Peschel trick tells you that this ρ1 is fully determined by the CHOP correlation matrix. What does CHOP mean? It means that I'm reducing the indices to the index that are associated with part 1. So it just runs, it stops, it goes from 0 to L. So this is where I'm chopping space. And this is a great simplification, because I'll be referring to numerical computations. This, in a sense, has exponential dimension, while this will just be a matrix L+1 times L+1. So this observation is important. Peschel's trick. What is the argument? I'll go quickly over the argument just to give you a sense. It's a fermionic system. The ground state is a Slater determinant, so all correlations could be obtained from the two-term correlations. Okay? And so the observables that are associated to part 1, so if A is associated to part 1, its expectation value will just be obtained by tracing the product of A by the reduced density matrix. And you know from Fick's theorem that this expression would factorize in terms of two-point correlations. For that to happen, ρ1 has to be of a free form, has to be the exponential of a bilinear expression, just to be able to use Fick's theorem. And then to arrange that, you need to arrange these coefficients so that these 2-point correlations are given by the formula that should give this expression. So you then establish a connection between little h, which is called the entanglement Hamiltonian, and the density matrix. And because so this is how you relate, therefore, h to c. And once you have h, you have rho 1. Okay, so this is special strict. You know everything about the reduced density matrix if you know the chop correlation matrix. So the space, well, I call PS the space of projector on the subspace, the chop subspace in space. Sorry, and you remember that go back, the full correlation matrix. Oops, no, it's the full correlation matrix. C roof. I will remove the roof when I'm talking about the chop one. The full is a projector PE. And therefore, the chop correlation matrix will be just sandwiching of the projector on energies with the projector on space on both sides. And this is the formula now. Once we have understood that what we really need is rho 1. Oh, yeah. So I need to go back. I recall that this is what we have. So the chop correlation matrix is given by this expression. And given then the relation, well, the von Neumann entropy is given by this formula in terms of rho 1. Rho 1 is determined by C. And so this would then give me the entropy. And we see that the task we have is to diagonalize this chop correlation, 2-point correlation function. I hope I've been clear. Okay, so to compute the entropy, the problem is diagonalize C, and C can be written in terms of this product of projectors. Now, this happens, it's great. It's lower than, yes?
So in the case that L is equal to capital N, essentially no chopping.
No chopping.
Then what is the C in that case?
Well, the projection, it would be trivial because the projection on
so that's just only the energy projection to the.
That's correct, but there's nothing to compute the entangled width, right? It's the full system, so then you have a trivial problem. Right? Just looking at the complement of the full system with its complement, which is empty. But mathematically, it's what you're saying. So we've understood the problem, right? It's to compute this C. This will give me all I want about the entanglement. But this will be, when I want to do the numerical computation, a full matrix. And if you go to high dimension, it's complicated because the eigenvalues will accumulate near 0. And here, the punch is that there's a useful information or observation in that there's a matrix T, which commutes with this C, but this T is 3-diagonal. So they will share the eigenvalues, they will share the eigenvectors. And so it's much easier to find the eigenvectors of a 3-diagonal, which is the analog of a second-order differential operators, than a full operator.
So what do you mean by 3-diagonal?
It's like, you recall the Hamiltonian. 3-diagonal is, there are entries, this is on the diagonal, the subdiagonal, and the superdiagonal. This is very important. And in terms of if you think of this, of a matrix like this, as a difference operator, so it goes one step to the left, one step to the right. If you take the continuous limit, it would be a second-order differential equation. And we know how to treat numerically second-order differential equation. This goes well, and it goes well also for a 3-diagonal operator. But if I have a full matrix, with eigenvalues accumulating at 0, this is hard to treat. So this is a technical problem, but one which is interesting conceptually. And this is what will bring us. So now I will do a digression. So we've understood our problem with respect to entanglement. Now for some time, I'll tell you about signal processing, a very classical problem that was considered in the 60s, but a very important one. And it led to wavelet theory and all that. And we will see that the root of the observation that I'm quoting is there, because there's a complete parallel between the two problems. Okay, what is this problem? You have it's also referred to time and band limiting. So we have a signal, f will be our signal, depends on time, and it's limited in frequencies. We'll take the band to be, just for symmetries, minus w to w. So it means that the Fourier expansion of the signal is only over these frequencies. I don't go from minus infinity to infinity, but I limit the frequencies. Okay, the signal, it belongs to that space, which means it is frequency, it is banded in frequencies. Then it's natural to want the signal to be also finite in time. All real signals are of finite duration. And so you would like to impose that. It is strictly banded in time. But this is not possible, of course, because this is an entire function. By Liouville theorem, it would be strictly zero, because if it's zero at on any interval in the complex t-plane, it would be zero. So the fellows at the Bell Lab then consider what's the next best thing you can do, and you ask yourself, how can I approximate the situation? And they ask, what is the band-limited signal that is best concentrated in a certain time interval? And so this is a variational problem, and it's easy. So you want to optimize or maximize this quantity here, you see, so I try to limit in the interval minus t to t, and it's an easy computation to see that this expression will be like this, and calculus of variation shows that the solution to that optimization problem will be given by solutions of the integral equation, which is up there, gf, you see this integral equation. You're looking for the eigenvalue. This is the Lagrange multiplier, which plays the role of the eigenvalue, with the kernel of the integral operator, in this case, the sinc curve. And it can be related to random matrices also. We could do also the Airy kernel and so on. I'm giving you the simplest case. And so, okay.
How general is this form of the kernel?
How general? It is this is the answer in the problem that I'm considering. If I'm just looking for, but you can have other situation where you're looking at the cylindrical system, or then you will have other kernels, Bessel kernels. It depends on the problem, but for the simplest Fourier problem I'm presenting, this is it. There's no, it's just a straightforward. You just put in the Fourier transform, and you have you exchange the integrals, the integration you get there. So in principle, that problem is solved again. You just need to solve this equation, but we face the same issue. It's untractable numerically. Eigenvalues accumulate to zero, and it just doesn't work. And this is something that engineers are facing all the time, and they use this observation of Slepian that there is a differential operator that of second order that commutes with this integral operator. So this is a remarkable fact. It's still called by many like the Slepian miracle, and a lot of people, like my friend Alberto Grunbaum, are trying to understand why it is so. From where is this coming from? And we've worked a little bit, so I'm telling some of the story that is associated with that. Okay, now let me explain the parallel with the problem of the entanglement. First thing is we can write this G, this integral operator, in terms of projectors. Let me call, there's a little bit of notation. If I project in the variable x on such an interval, okay? So this is, it would just be written as a form of theta function, where theta is a step function. This will denote the Fourier transform from little f to big F. So this projector will be the same as the notation. So I apologize, but you see, I have pi of L. This is associated to the interval, and the variable, the space on which it acts, arrives here. So all this is saying, this is the interval W. This was the projector I was interested in. P is the variable. And then I can take the Fourier transform of a projector associated to an interval big T, but in the time variable, and I Fourier transform to bring it to the momentum variable. And it's easy to see that with this definition, that this integral operator with the sinc kernel is just, you chop in momentum, you chop in time, you chop back in momentum. It's easy to do. So we'll do the computation. First parallel, very similar to our chop correlation matrix. Now, the existence of this second order differential operator, this is one thing we've contributed to, can be traced to an underlying bispectral problem. This is something that arises all the time in the theory of orthogonal polynomial in integrable systems. What is that? This is an instance of a situation where you have a function that you could view as a function of two variables that satisfies two eigenvalue equation, hence the term bispectral. One through the action of an operator x acting on variable x with eigenvalue omega that depends on the other variable, and the other with y acting on the variable y with the eigenvalue lambda depending on x. And well, this is obvious. We wouldn't even think that this complicated framework, but it is there for the Fourier functions, because obviously for these functions, second derivative in t will give p squared, second derivative in p squared will give t squared by total symmetry. Okay, but this is the simplest instance of a bispectral problem. And how does that lead to t, you will ask me? Well, to each such bispectral problem with x defined in terms of two operators, x and y, you can define a Hoyne operator by this expression. It's the most general bilinear expression in the two operators x and y that define this bispectral problem. The taus here are constants. Why do we call this a Hoyne operator? I will not really tell the story. Is that if you take x to be multiplication by x and y, the hypergeometric operator, that would have, say, Jacobi polynomials as eigenfunctions, the Hoyne operator that I've defined, or where I've given an algebraic generalization, will become the ordinary Hoyne differential equation, if you're familiar with that. So that's the root of it. But let's go back to the Fourier case. So where x is second, and I need to decide in which representation I am. So, and here I will take the frequency representation. So in that case, x is second partial with respect to p, and y will be multiplication by p squared. And so my definition, I will simplify a little bit all the constants I add, and if I set these constants, the Hoyne operator will just be anti-commutation, commutation of the two operator, the operator, one operator, the other. I could have had the constant, but I threw that away. And so it will be of this general form. It's a second order differential, first order term, and a constant term, with these expressions for A, B, and C. And now let's see how it's possible to have something that commutes with this G. since G is written as a product of projectors, if this operator commutes with each of the projector, it will commute with the products. So let's just do quickly. I'll go quick, but I just want you to see that it's not so complicated. If I commute this W, an operator of that form, right? I know what A, B, and C are. We'll come back to that later. But I commute this operator with the theta function. Well, it's easy to see that I have a second derivative term. So it will hit the theta function, will give me a delta, and then I will still have a first order derivative. Or I commute with the second derivative, so I act twice on the theta function. So I will have a delta prime. I transfer it on the function in front, so I will have these terms. And the V comes from the part B is in front of the first derivative. Okay, not difficult to see that this is what you have. And if you want this to be 0, okay, so I want W to commute with this, well, you know, I need AP to vanish when P is equal to W, and I need to have this relation when P is equal to W. So this, I have these two relations here. And it's easy to see that if my real projector is the combination of these two theta functions, then I will have see, I've just done the computation for 1. If I now do it for 2, for the one with the plus W and minus W, I will have the condition. The conditions must be realized for both plus W and minus W. And in view, sorry, I have to move from one slide to the other. Try to just remember that. And so you see, if you do that in the function, it fixes nu. Nu has to be plus or minus W squared. Sorry, W squared. It's valid for plus and minus, and tau is equal to 0. So in other words, don't mind all the details, but it's that simple. What happens is that you fix the parameters. And the other condition, so you've shown now that this will commute with one projector, but the other condition is the same because the other projector is obtained by Fourier transform of a projector of the same nature. And because we have a symmetry between P and T through Fourier transform, it will, in a fashion similar, it will fix the other parameter to be T squared. So the upshot is that the following thing, that the commuting differential operator is obtained by first writing down the Horn operator associated to the bispectral problem. You write the operator, so you have some parameters arising there, and all you have to do then is to fix the parameters appropriately. This gives you commuting number. Well, after this long digression, I come back to my entanglement problem. And there's a remarkable parallel with the two problems. Taking the system, the first step we did, we took the system as the ground state. Well, we had to restrict the energies to do that. This is akin to band limiting. We have one limitation problem. Establishing the bipartition to look at entanglement, I had to chop in space. This is the same as time limiting. The problem was to diagonalize an operator which is written in terms of projectors associated to the two choppings. This is analog diagonalizing G. And so the observation that there was a commuting operator is rooted there. So the similarity indicates that there will be an operator T, this is so, that will commute with the two projectors, PS, pi S, and pi. Okay, but to do that, you remember that we needed a bispectral problem. And so we will then look at chains that have this feature of having an underlying bispectral problem. And an easy way to do that, you remember that the chain was diagonalized by some orthogonal polynomials. And we know that all the orthogonal polynomials of the ASCII scheme, I don't know if you're familiar with that, but there's the ASCII-Wilson polynomials, the Raka polynomials, they are at the top of a whole set of polynomials. They are all bispectral. To be orthogonal, of course, they need to all, this is a theorem, Fadal's theorem, obey a three-term recurrence relation. That's a must for any orthogonal families of orthogonal polynomials. But those I'm mentioning, those in the ASCII scheme, all obey either a differential or a difference or Q difference equation, and they are all bispectral. So if I fix my system to be one which is diagonalized by some families of these polynomials, or some of these families, then they will be, we will have an underlying bispectral problem. What does it mean then? Is that in addition to the lambda that defines the Hamiltonian, there must be another operator x, which is such that it is diagonal on the space basis and three-diagonal in the energy eigenbasis. Because why? Because this will imply that these overlaps over these two bases will obey a difference equation that comes naturally from, you see, acting on the left or acting on the right. On the left, I'll get the eigenvalue, and on the right, I'll have the three-diagonal action, and this would give me this relation. And this is analog, this is in addition of the lambda, which was diagonal on the energy, of course, by definition, eigenbasis, and three-diagonal, this is how we define the Hamiltonian. And this led to this three-term recurrence relation. So 1 and 2 are the bispectral relation for our problem with these properties. Lambda is diagonal, I repeat, in the eigenbasis, three-diagonal in the space, the position basis, and vice versa for x.
So the bispectral means two arguments, or?
Yes, because phi will be viewed as a function of two discrete variables. One is the energy, k, the other is the position, n. Both variables here are discrete. It's a discrete problem. But you see, in one case, I can do this as a three-diagonal operator acting on the variable n, right? Because shifts n by +1, n stays there, n is shifted by 1. The action of this operator on the right gives me an eigenvalue that depends on n, and the other one is here. So you see, now I shift the energies, plus or minus 1. It's an operator acting on that space, on the energy space, and it gives me an eigenvalue that depends on.
So is it a result of the nearest neighbor interaction, or any two?
No, this is an assumption. See, I'm assuming that there will be my problem to start. I start with this problem. This is the diagonalization of the Hamiltonian. But I'm saying that I would like to now have a problem that commutes, a problem that is such that there will be an operator, a point operator that commutes with the two-point correlation matrix. When can I have that? I can have that whenever the polynomials that arise here from the from diagonalizing lambda belong to the ASCII scheme. So it's a huge class of polynomials, but it's not any polynomial. It's not any orthogonal polynomials. These are hypergeometric polynomials.
Well, what is the corresponding relation of equation 2 in terms of your information, time, and the frequency case?
Well, equation, you see, equation 2 is just, it is because the chart, I only look at energies, the K here are Ks that belong to the are momentum that belong to the Fermi sea. So it's related to the chopping in frequency. And the other is related to space.
So your model, do you have scattering function?
This is no. I'm not looking at scat, but this is an interesting thing. But it would lead us to somewhere else. Okay, let me try to wrap up. So I will have a commuting operator. How to do that? So I start the same, machinery. I will write the Hoyne operator. I take it again special. I don't forget the commutator part, but something bilinear in these, just for the sake of making the presentation easier. It's easy to see that T will be tridiagonal because in both bases, because it's a combination of two. One is diagonal in the basis, but tridiagonal in the other, and vice versa. So their product will be tridiagonal in both bases. In other words, if I act with T roof on these bases, it will have the following form. I'll just focus on the +1 term. Okay, so look, I've computed it. And then I want to show that if, when n reaches big M, it should stop. If I wanted to commute with the projector, because it should project a space on which pi projects. But you can easily see that if you pick little n to be big N, well, you will fix nu to just annihilate the sum here. And indeed, this is what we should do. So if I put nu, if I put nu equal to this combination, and sorry, I misspoke. I want to preserve the space on which the projector in space project. It project on the first L+1 state. So I said big M, but no, not big M. N+1 should be L. Should not go outside of the first part. This did not use the right letter. Okay, and so then if I just fix the parameter to be related with, remember, L defines the span of the states of the first part. And similarly, mu to be related to these energies where the omega k was spanning the space of this energy states in the Fermi sea, then both subspaces will be preserved by T. So it means that they will commute with the projectors. And if it commutes with the projectors, it will commute with the full correlation matrix. And so T with these restrictions of nu and nu will commute.
So here in so mu and nu seems to be kind of chopping parameter either in the
They are related, exactly.
frequency.
Exactly.
But in your previous analogy, I guess in the information case, was it very similar? So when you fix the parameter mu,
yes. So you see, energy is like frequency, right? And mu is related to energies. So let's go back. So you see, mu was related to the frequency, to the limit of the frequency. So it's very, very simple. It's in fact, you could just believe it's the same problem. Because the one key thing was to understand that the essence of that is the bispectral problem. This is part of our contribution. Okay. So we have this commuting operator, and this gives it in some detail. It will be tridiagonal. If we know, and then we know it all. The coefficients are given. Okay. I'm going very slowly, but let's just give an example. The simplest chain we can imagine is obtained by taking these parameters. This leads to the Kraft-Trick polynomials, and in particular, if there's a parameter here, and if we take p to be equal to a half, then this is the form that the three-diagonal matrix here, then we can do the computation. If we take the space to be the half chain, so we split it in half filling, just to do the most simple case. This will be the entropy. And well, there's a lot that could be said about that, but there's this wiggling, which is interesting, and we're still studying that. It seems to be related to underlying charge symmetries. But in any case, you can find the results.
So Lajian does not converge.
It does not converge, no, but it will give the usual conformal field theory limit. It will be okay. Now I have to make some choices because I went slowly, but I hope this was an interesting thing to see, this parallel between this classical time and band limiting and computation of entanglement chains. The observation that comes here, and maybe I will not explain it in great detail, but is that the next step is to think, okay, we've been looking at chains, but there are other systems. I could put fermions in more complicated geometry. And the first, more complicated, but not so complicated, would be the hypercube. What if I consider the hypercube and put fermions at the vertices of the hypercube? And what I explain here, so is what is the hypercube? Well, it's the vertices can be viewed as a set of strings of n bits. You will, with each vertex labeled by 0 and a string of 0 and 1, so like this for the square. Okay, here I have 2 bits. And I can view that as the tensor product of the complete graph in 2 vertices. The adjacency matrix is if I have V vertices, is the V by V matrix that has a 1 if 2 vertices are connected. So here, you see, the adjacency matrix would be given by the polymatrix sigma x. What I'm explaining here, and I will skip that in the interest of time, is that you can see that this problem of fermions on a hypercube projects if I consider all the vertices that are at the same distance from a fixed vertex, it projects to exactly the spin chain I was describing, the Kraft-Trick spin chain. And so the computation is very simple and was written there. So the suggestions that come from this observation is that, and it might be interesting to look for fermions on graph, and given the right symmetry of graph, the hypercube is a graph with a lot of symmetry. In fact, if you look at distance regular graphs, this is the name, you could use what has been developed to compute the entanglement of these graphs. Okay, and then comes the story of association schemes. I will not have, in 5-10 minutes, I will not be able to explain all that, but I hope I've been clear about the concept of adjacency matrix. So you have a set, a graph is a set of vertices and links between vertices that are connected. You use the characteristic vectors associated to each of the vertices, So it's, let's say it's capital, this V to be the number of vertex. So I have matrix A would be a V by V matrix with zeros and one depending on which vertices are connected. An association scheme is a set of adjacency matrices. It's a family of adjacency matrices. So you have, so for the upper cube, you would connect vertices that are at Hamming distance 1. So the Hamming distance is defined by the number of bits that differ. Okay. But I could connect vertices that are at Hamming distance 2, Hamming distance 3. So we then have a set of adjacency matrix. And this would form, I'm giving the formal definition, but they will obey the Bose-Messner algebra, which is here. So the product of two adjacency matrices will be given as a sum over linear combination of the adjacency matrices. It means that you can go anywhere in the graph by first hopping from one vertex by a step of 1, then a step of 2. You will be able to reach that by a combination of steps. And this is very important in, so what are the elements there? So these matrices are diagonalizable, so you can define the projectors, the projectors on the eigenspace of these matrices. These are the E associated with the idempotents. And then you can introduce a concept. I'll just mention the thing so as to, you've not seen that. You can use introduce the dual matrices, which are defined like this. A tilde, these are diagonal matrices, AI star, obtained from the idempotence EI. So the VV entry will be, having defined a reference vertex, will be the V0V of the idempotence. And the E star will be given in terms, similarly, of the adjacency matrix. These E star are also projected. The Terwilliger algebra, which is very important in that field, is the algebra. You see, I told you that these span the Bose-Messner algebra. If you adjoin the dual matrices, they span the Terwilliger algebra.
So, I mean, previously you seems to be relied on the essentially Fourier transform and also three-diagonal matrix.
Yes.
Such thing.
Yes.
And the association and that
Yes.
reward is replacing those.
Yes. You see here, one important thing I failed to mention is that the adjacency matrix will play the role of the Hamiltonian for a system of fermions on the field. And now I will put this Hamiltonian in the within an algebra. And more than that, what I'm seeing is that the commuting or an operator or the correlation matrix will belong to this Terwilliger algebra. So this is why I'm mentioning that. If I'm looking for a system of fermions on the graph, the critical two-point correlation function, which is the thing I need to diagonalize, will belong to that algebra. And so the strategy is like this. So I identify the Terwilliger algebra, and then I will use representation theory to find the irreducible decomposition of the regular representation of this algebra. And this will bring me back to chains, to the systems I've looked into. And then I could simplify enormously the problem. And just maybe I will close in just a few minutes. So I understand that what I'm saying is obscure, I'm just stating. But if I look at the entanglement on graphs of the Hamming scheme. So this is the family of the hypercube and the generalization of the hypercubes where I connect vertices that are related by distance 2, by distance 3, and so on. I told you that this, I'll just return to that just for the illustration. Simplest case of an hypercube is a square. And so you see that it's the tensor product of K2 with itself. But in any dimension, I would take the nth Kronecker product. Okay, so let's have that in mind. So I want to illustrate what the Terwilliger algebra will be, and it will be in this very simple case, an algebra you know very well. It's extremely simple. So you see, for the complete graph, 0, 1, well, there's two vertices, so the adjacency matrix will be 2 by 2, and it connects 0 and 1. So it's one here, it's one here. This is sigma x. And so, and because the hypercube is just the tensor product d times, so this will be A1, the Hamiltonian of the system. And the dual matrix, well, you go through the steps. It's simple. I will skip them. But you find that the dual matrix is sigma z. And again, just knowing that the hypercube is just by tensoring, A star will be this algebra. So the Terwilliger algebra in that case will just be SU2. So for those systems of fermions on hypercubes, the story is that I'm explaining a little bit about the reduction of the representation. But if I have my system in a set of neighborhoods, no, if I'm looking for fermions on the hypercube, I need to specify a bipartition of that. If I take sets of vertices that are at given distances from a reference point, then using this knowledge that the correlation matrix will belong to this SU2 representation by the analysis that I've just glossed over, I can just use the SU2 representation to reduce the problem of looking at the entanglement on hypercube. It will reduce to a combination of fracture chains like the one I presented. This is saying what I was saying. So I apologize, but maybe it's always better to go slowly at the beginning and not cover everything. So I apologize for glossing over the last part. But the theory of association scheme is one core part of algebraic combinatorics. There's still many, many problems. And in fact, we've been able to solve some problems looking at entanglement questions. But the scheme it's always like that. So there's something called the P and Q polynomial class of association schemes. They are in correspondence with these polynomials that I mentioned, the ASCII scheme. But the Terwilliger algebras are not all identified, and certainly their decomposition ends not completed. So we're in the process of doing that. And talking about problems that we can be looked at, we could also imagine using orthogonal polynomials in more than one variable. When you use, as I did, orthogonal polynomials in one variable, you're looking at chains. But we could look at fundamental systems, say, that are on a two-dimensional lattice, and then you would need to use orthogonal polynomials in more than one variable. This is also being pursued. And you recall the wiggles in the entanglement. We now understand that this is related to a resolution of the entanglement from a symmetry perspective. This is also this intense study now about that, is if systems have symmetry, how does entanglement behave with respect to certain symmetry sectors? That is what I mean by symmetry resolution, and then something called higher dimensional association schemes that would have bearing also on this problem. I thank you very much for your patience and for being here.
Questions? Besides the computational scheme you talked about, which is very interesting, what do we learn about entanglement and free filament?
Yes, it's two. There are these two things. There are the physical questions and also developing tools to study the entanglement of maybe more physically relevant problems. So with respect to the tools, this is what I focused on, developing all the apparatus. With respect to the physics, well, it's the most, the most striking observation are these oscillations that we found. And this is not fully understood. We believe that we're on the way to understanding that, and it would be related to this symmetry question. So there's a U1 charge that, so the pattern seems to follow the profile of a U1 charge, which is a number of fermions that you have in the system and its average value. And this is what leads us to believe that there's a connection between the symmetry. So that is under scrutiny right now, is raising significant attention.
Do you see the period of that wiggling?
Well, there are also those questions putting periodic boundary. These
no,
are,
I mean when it wiggles, what is the period?
The period, this seems to be related to the period of the average value of the number of particles. So, but I'm saying that this is a hypothesis. We are working on that to confirm that this is.
So as far as about entanglement entropy is not yet it's not observable physically. No experiment succeeded.
This is measuring entanglement is a complicated story. It's more, entanglement is a way of quantifying the degree of correlation of a system. So it's a theoretical tool, right?
But this wiggling may indicate wiggling of other physical.
Then we should be able to yes, there would be something that is measurable that we could relate to this theoretical concept. And indeed, this is the purpose of physics.
I have two questions.
Yes.
One is that behavior, independent of B field in your Hamiltonian. If we turn off that, what happens?
Okay. Yes, because no, it is not. It's more complicated. You see, I've shown you a simplified case, but let's see. Yes. So when I showed you this case, when P is equal to a half, so this term disappears, and the B field is constant. So then I can just scale it away. But we have the formulas, but I don't have to. It gets more complicated. But this,
Another one is those past-chair street you called.
yes.
Can apply to long range chain. Only nearest.
Yeah, that is, I need to, I'm not sure, I think so, what is key is that it is free. So you're saying, if I have more than the nearest neighbor
Yeah.
couplings.
Because there's also relevant with the super Young speech.
Seems to me it should work. The key thing is the fact that all correlations can be, that you have a fermionic free system. So you have, all correlations can be expressed as as products of two-point correlations. That's the approach. I would need to go over by offhand like this.
Any other question from online? Okay, so if there's no question, let's thank.
Thank you. Just
Yeah, maybe secretary can. But
Very interesting, but I have to go for
Yeah.
my next. So I hope you enjoy your stay.
Well, thank you so much for coming.